So differential equations are the most important application of calculus. It's not the only application. It's not the only place differential equations are used, but for many people, the reason they're here is to learn about differential equations. So differential equations means that's an equation that connects a function with its derivative or derivatives, and if you take the qualitative approach, so which has become very, very important in my thinking about differential equations over the years, is you think about growing and increasing and decreasing, and you can get an awful lot of good insight into differential equations by thinking about them that way. So I've gone to the trouble of writing up how I think about differential equations, which is part of the calculus book I've been now working on for way too long, less than a century. But so I've put these things on Moodle. This computer's so slow, I'm afraid I'm going to totally waste your time if I show them to you, because it'll take so long for this computer to get its act together. And so, but I believe they are there on Moodle, and so that is where we're thinking about things. And so today and Friday are definitely going to be differential equations days, and we started that a little bit yesterday. Thursdays are bad. I don't get to do calculus. And Monday, Tuesday, Wednesday, Thursday. What am I supposed to do all day? And then, but we'll continue to look at things. And so, it's hard to pick out the right WebAssign problems. And the sequence that you're in, Calculus 1, Calculus 2, where you are now, Calculus 3, and the Calculus 4, we don't call it that, we call it differential equations. And most of the engineering majors take that. And so that's where you go into a lot more depth and detail. But it's not something that you can kind of do you can't do it by memorizing it all. You have to develop a feel for what's going on with these things, and that's really my goal for how we do things in Calculus 2, is to start to develop that feel. So I think what we ought to do is just kind of jump in. Let me. Okay. Oh, wait. So this is where we were yesterday, and what I started to do, and we kind of got rushed a little bit at the end, so I want to make sure that we get unrushed, is look at a differential equation. So this is a simple one, and a lot of these can be solved exactly. And we will do some of those. There's one technique that we're going to do for solving exactly, or maybe two. Anyway, so here's an equation connecting a function y and its derivative, dy by dx, and it's got some other stuff in there as well. And so the situation here is that you have to think about y as being a function. Of course it's a function. It says so right here. So y as a function, and what we're not, but we don't know exactly how. We don't have a formula for y. We don't have any description of y. We have a information about its behavior, so we know what its derivative is. And so what we're saying is the derivative, if you pick any point in the plane other than where x is 0, then I don't know what y is there. Well, I do know, but it doesn't help me much. But I know what the derivative is there. And so that is a little piece of information about the function. If you go to a different point, you get a different derivative. Go to a different point, you get a different derivative. You go to a different point, you get a different derivative. And because we know the tangent line approximation, we know that, and that's what this part of the picture is up here. We know the tangent line approximation, so we know if we know the derivative at a certain point, and we know the point, obviously, then we have a point slope form for the tangent line, and the tangent line stays close to the solution for a little bit, and that's kind of a judgment call. It depends a lot on what's going on with the function. So if you look back at this picture, this is from yesterday, the tangent line's in blue, and the curve that we don't know the curve, but if we did know it, it would be in black. That didn't come out right, did it? The black curve, we don't know the black curve, but we know there is such a thing. But we know also that the blue line and the black curve agree, within the thickness of the lines for, a little bit. And so what happens is you say, okay, so if we go back down to this picture, I say, well, at a point like this, so that's got some coordinates. I don't know what they are. But, well, you can kind of eyeball them or whatever. Well, you can say y over x is, I don't know, y is pretty small compared to x as far as an absolute value. And so, maybe y over x is 0.6 or something. So y over x is minus 0.6. And so this red piece here is not the solution, but it agrees with the solution pretty closely for a small bit. So that's why I've just drawn a little piece of it. And then same thing over here. And as you work your way around the plane, you can draw a little piece of the solution and then see what's going on as far as what the solution really looks like. So, and this is all based on the tangent line approximation. So the tangent line approximation is one of the most useful things that our species has ever come across. And so this is where we're going to use it. So we don't know this function y, but we're starting to be able to tell a lot about it. So, so that's the situation that we're in just for now. Okay. So let me, I'm sorry. So in WebAssign, they call this direction fields, and you've got problems where they show you do have, yes? I'm not making this up?
Say that again.
Problems where they show you direction fields and ask what?
In Calc 1?
No, right now in WebAssign.
I don't know that in WebAssign. It's the arc length assignment this week.
Oh, okay. Man, they messed me up. They messed you up. So they messed me up, I messed you up, and I apologize. But, okay. But this is, when's this one due?
I think it's Friday.
Not that long, but yeah, Tuesday.
Oh, yeah, okay, so we're about right, yeah.
It's not this one. Okay.
I think it's 9.1. So yeah, 9.1 is due on the 28th, so that's a week from today, or a week from yesterday, and 9.2 the later that week. That's about right. Okay. Well, let's get on them. I mean, if you're going to have them due, we better get on it. Okay. So, so you may not have looked at it, but it is there, and so there's the deal. So what I wanted to do is do another example of a direction field like this, and then just to help you wrap your mind around this picture, and then look at a method for doing approximate solutions. It's not the best method, but it's a method, and it's based on the tangent line approximation. So that's why I make such a big deal out of it. Okay. So what's today? So it's fall now, right? We had the harvest moon. I can make that a little bigger. So someone comes up to you and gives you, it's going to look like it's a very similar equation. So the derivative of y is the negative of this fraction, x on top and y on the bottom. So that looks pretty similar to what we just had. The previous one we had was y over x. So this is similar, and in the days when we taught more geometry, I mean, like this was going out when I was a high school student, so I don't think you saw that much of this. Someone who's really an ace at Euclidean geometry would look at this and say, "Oh, that's a circle," because and so this is the kind of stuff that you can bring in. So here's the slope of some curve, right? The derivative, and if you look at the point xy, so here's a little set of axes. If you look at some point xy, and you draw the line from the origin to the point, that has slope just rise over run. So the rise is y and the run is x. So that's actually looking at what we just looked at. So, but now we have that the slope is -1 over that. So if I call this m, and if I look at a perpendicular here, the slope on this perpendicular, it's too hard to write perpendicular, so I'm writing the perpendicular symbol. Otherwise, we'll be here all day. So the slope of this perpendicular is -1 over m. And in that case, that is minus the fraction x on top, y on the bottom. So if you look at this equation geometrically, you're saying the slope of the curve at some point is perpendicular to the line from the origin to that point. So, because that's a general property of perpendiculars. I'm sorry, and you probably heard that someone mumbled it under their breath and didn't emphasize it. But that's the relationship between a line and its perpendicular is this -1 over m situation. And so And so what you're seeing here is the slope of the line to the origin is the negative reciprocal the slope of the curve. Negative reciprocal of slope of line to origin. And that's a characterizing property of circles, that the radius and the tangent are perpendicular. So, and you know that because if you lay a coin on a table, here's the center of the circle, and here's the radius, and that's perpendicular. So the reason I do this is I want to check the reasoning about what we do with the direction field. So the direction field is I'm going to say, well, at every point, what's the slope of this curve I'm aiming at? And the curve being the graph of y. It works out in this case, y is not a function, as you'll see in a second. But we can work out what is going on, and that will give us something to compare it to. Plus, there's this reminder about the relationship between slopes of lines and their perpendiculars. So, okay, so let's do the direction field, and here's the situation. First, I'm going to do kind of vaguely the sign of what's going on, and I've shaded part of this in a very light red. I feel like a designer. I think a very light red will bring out the danger in working with fractions. No. And so, and let's look at the signs of the derivative of y. And so, in this upper right-hand quadrant, the derivative of y, well, x and y are both positive, and so the derivative of y is negative, because you negate it. So in these red regions, y prime is negative. You can say negative all you want, and then the idiot writes positive. Excuse me. And if you look in this lower left region, both x and y are negative, so their quotient is positive, but then we negate it. So you're looking at y being a decreasing function everywhere in red, and y being a decreasing function everywhere in red. So if you have your circle centered at the origin, if you're looking for a circle, the graph that you see here on what I'm telling you is the solution is, well, look, the tangents all have negative slope in this portion, and the tangents all have negative slope in this version. Or the graph is decreasing, and the graph is decreasing. And so these are all consistent. And I'm getting this just by looking at the signs. I mean, so I know things in this red region, all the slopes are going to be negative. And in the other region, which I guess I'll do in blue because that's the other color I have, sorry, it takes longer to shade this in, though. Y prime has to be positive. So in these blue quadrants, x and y have opposite signs, so their quotient is negative, but then we negate it. So dy by dx is the negation of that quotient. So dy by dx is positive in that quadrant, in those two quadrants. And if you look on a picture of a circle, that is in fact what you would expect. So in the blue part of the circle, that's the graph of an increasing function. And the other blue part of the circle, that's the graph of an increasing function. Now this thing also, the slope of the tangent becomes infinite at this point here, but that's okay. And I'm sorry, I need to, when I talk about the blue quadrant and the red quadrant, we're not supposed to talk about politics anymore, are we? Okay. We've got the blues and the reds. Okay. So let me fill in. This is actually going to be some kind of calculation here, where we can fill in what's going on with this function y. We don't know what this function y is, but now we know an awful lot about it. This information right here is enough to tell you that that you may not have a circle. You might have, something kind of wickety-whack like this, where the graph is increasing. That bump shouldn't be there. Back is steaming. Ooh. And so you're thinking about some kind of oval there. Now you could also have an asymptote out here. Y prime's negative, y prime's positive. But so this is another possibility. This is from The Little Prince. That's the boa that swallowed a cow. So these are possible shapes for the graph of y, just based on the information we have. It's not, you don't know nothing. So there's the deal. Okay, so we're going to fill in the direction field. And the way that you do that is you pick a point. So I'm going to do like 1 comma minus 2. And so the y prime there is minus x over y. So 1 over minus 2, which is a half. So the direction field looks kind of like this. It goes through that point, and the slope is a half. I'm just eyeballing the 1/2 part. And so there's the situation. If you look at 1 minus 1, now the slope is 1, so that's about like that. And if you look at 2 minus 1, so you can kind of start to fill in a grid with these things. You can say, well, let's see, x is 2, y is minus 1. So the slope here is 2, that's steeper.
This is still for the graph y over x, right?
No, this is the graph of y.
Okay.
But we're kind of piecing together. Oh, I'm glad you asked that. That's important. We're piecing together the graph of y because we know how the derivative of y is related to the point x and y. So you get a little piece everywhere. So, sorry, I'm pointing up off the screen. So this is the relationship that we're given, and so now we're trying to piece together what we can about y. So yes, thank you. Good point. So you can kind of do this on a grid. So for example, at 1, 1, you plug in for x and y. The thing is, you don't know the function y, but you know one value. You know, I know right here y is 1. So what does the rest of the function look like? And so you can say, well, the slope there is -1, so you're going to be looking at something like this. And let me just kind of fill out the corners of the box here. If you look,
Do you mind if you can scoot it over?
I'd be happy to. So if we look at the point -1, 1, the slope of the tangent there is 1. So we know this is very close to being a little piece of the solution curve. And I'm going to do the same thing at -1, -1. And now the slope is -1.
Wait, how does, if you have the graph negative x over y, you had -1 and -1. Oh, I know, yeah.
Okay. So what we're seeing is little pieces of the solution curve. So what actually happens, and this has a method to it. So let's start at. Can I just kind of eyeball draw in a bunch more? So the thing is, for this particular one, the direction field depends on the slope of that line through the origin. So we're seeing all these -1s. You get a vertical direction field, vertical, vertical, vertical. You get horizontal when x is 0. And these are steep, and these are steep, but with the correct sign. And that's a little bit messier than I had in my head. Let me just kind of clean it up. And I'm cheating a little bit. I'm just going to do... So you pick a bunch of points, and you do these little pieces of the tangent line, and you start to get a direction field that looks... I'm sorry. And the direction field looks something like this. That's a little rough because it's hand-drawn, but there it is. So this is the complete direction field. By golly, that looks pretty circular to me.
How did you get y prime? I must have missed that.
Y prime is -x over y. So I pick a point, and I calculate -x over y, and that's the slope of the tangent there. Yeah, it's like magic. It's like you're getting something for nothing. You're getting the derivative without going through all that derivative stuff. You're just saying, oh yeah, it's -3/2. So. Uh-oh, which was the inside, which was the outside? Sorry. So this is giving you a lot of insight into this function y. You don't know this function y. You know its derivative. And you've got some insight. And the insight comes from thinking in this kind of qualitative way, not quantitative. It's like the slope of the tangent, positive or negative, big or small, or steep or shallow. And you get all kinds of interesting stuff out of this that that happens just by thinking that way. So Let me run one more of these by you, because this is just such a useful way to think about differential equations. So this is all working with that same equation, and this is one that we can, we can solve exactly. We're not going to do it today, but probably Monday, maybe Tuesday. We can solve this exactly. There's a technique, and you'll find out that what you get is a circle. And so this is all, everything's kind of coming together. But you kind of knew that already just by looking at the direction field. So let me run one more by you, lickety split. I'm kind of using standard notation. This is called the logistic equation.
Is that L minus y or perpendicular minus y?
L. Yeah.
Okay.
It's in a formula. So, and we want K and L to be positive. And so I'm going to make a funny graph. You're just going to die laughing. No. And the graph is this. Y as the horizontal axis, that's like the input, and Y prime as the vertical axis, that's like the output. And you can see there's a relationship here, right? Y prime is something. Well, this is describing an upside down parabola if you think of y as being the variable. The real variable here is x, but if you just think about this piece of it and having y as the variable, what you're seeing is this relationship between y prime and y. So y times L minus y, if you think of y as the variable, that's the graph of that is an upside down parabola. That's one of the basic shapes. And you've got the roots are 0 and L, and so there's the graph. And what that tells you is this. That says that y prime is greater than 0. That's important. That says the slope of the tangent line is positive, or that y is increasing. Y prime is greater than 0 if y is between 0 and L. And y prime equals 0 if y is equal to 0 or y is equal to L. Right, you plug in y equals 0. You get 0 for the whole thing. Or if you plug in y equals L, this factor becomes 0. And so y prime is 0. So that's now a constant. So we're talking about this stuff here. And so we can, that's enough to graph it. And not graph to build a bridge, but graph to understand what's going on. So let me just do that. And I'm going to say here is the, here's y. I don't know. This is where y is equal to L. And then someone's going to tell me why I'm being sleazy. This is where y is equal to 0. And we've kind of chopped the xy plane into 3 pieces. In the part where y is bigger than L, y prime is increasing. I'm sorry, y prime is decreasing. In the part where, so that's this part of the parabola. And then y prime is decreasing if y is less than 0. and y prime is positive, so y is increasing if y is bigger than 0. So you get a function that is decreasing toward a line it can't cross. If the graph ever hits y equals L, the derivative is 0. That's it, no more change. Or if the graph hits y equals 0, then y prime is 0, the derivative is 0, constant function, no more change. So you can't hit these lines. But what you can do is say, you know what, the solutions look like this. That's just a few of them. So if you start above the y equals L line, you have a function that's decreasing. And if you start below the y equals 0 line, you have a function that's decreasing. And if you start, and you can say a little bit more than that, but let me just finish off this 3 thing. If you start somewhere between 0 and L, the function is increasing, but it can't cross y equals 0 and it can't cross y equals L. So it has to have this kind of shape to it. And so there it is. Those are the solutions to this differential equation. So it depends on where you start, and you get, if you start really big, it decreases down to this level L. And if you start really small, anywhere negative, it just goes negative forever. And if you start between 0 and L, we're always increasing, but because of the constraint of not being able to cross these horizontal lines, the thing has to level off as you approach one of these are asymptotes. So this is, except for one little sleazy bit, this is a solution to, these are 3 different solutions to this differential equation, 3 different functions that satisfy this equation. So, and you know, the most complicated thing we did was graph a parabola given its roots. That's the most complicated calculation we've done here. But now we have this very almost detailed set of solutions, except for one tiny point where I've been sleazy, and now someone's going to tell me how I've been sleazy in the context of this class. Don't tell me how I've been sleazy outside of class. Sleazy. This is sleazy. This is correct. What's missing on this graph? Well, can you spot the 5 differences between this graph and the other one? Well, let me start saying what's going on here. I know the vertical scale because I know that this distance from the lower asymptote to the higher asymptote, I know that distance is L. And every graph has to have a scale. So people are nodding their heads. So which scale is missing? Well, we don't know the horizontal scale. This could be x is 1,000,000. This could be x is minus 1 over pi. So there's no horizontal scale. So that's the sleazy part. So that's what keeps it from being a complete graph. But man, there's a lot of information in this. So, so this is the logistic equation. Let me tell you something that you could do that we don't have time to do. I might do it on Friday if there's popular demand. But when I say that, no, it never happens. And we might have to do this anyway. This, if I know y prime has this thing, now notice this doesn't depend on x. That's partly why we don't have an x scale. So it doesn't matter what x is. All the y primes are the same as you move horizontally. And so that's partly why we don't have the x scale. You could just move it. But this is enough information that not only do you know y prime, you know y double prime. And so that tells you the concavity, and you have to use a technique from Calculus 1 that, in my experience, is not emphasized enough. How many times have I said that? But the technique from Calculus 1, I'll just write down what it is. It's called implicit derivatives. So implicit derivatives, you treat, when you're taking the derivative, you say, oh, this is a product, I'll use the product rule. But y is a function, so the derivative of y is y prime. And so you get all this stuff with y prime, and then you substitute this back in. But I want to get started on something else. So here's the situation. This is called Euler's method. And this is for an approximate solution. Now, unfortunately, fortunately, I guess for us, Euler was very prolific, and his collected works are like 57 volumes. So there's more than one Euler's method for doing lots of stuff. I mean, so that doesn't really pin it down. Oh, Euler's method, what's that? But here's the here's the situation. So what you do is you pick a point. And you pick a horizontal distance h. Now, you use the differential equation to find the equation of the tangent line at that point. And then you follow that to a plus h, so you get an estimate for what y is there. You use the tangent line approximation. You say, well, the curve, I don't know what it is, but I know it's close to the tangent, so if I pick a small distance, this calculation that I get on the tangent line will be very close to the actual solution, and then you repeat. So let me just do that a little bit with this. We don't have a lot of time. So let's start at, I don't know, 2 comma 1, and we'll let h equal 0.1. H should be small. So the slope, I'll call it m, call me crazy, is, that goes back to the differential equation. The slope is minus x over y, so the slope is minus 2. So what we do is, well, this tells me that y of 1.1 is approximately, well, I'm just following on the tangent line. The slope is minus 2, and I'm going out 1/10, so I'll go up minus 0.2. So now I have a new point, 1.1 comma 0.8. So get the equation of the tangent line. To do that, you need the slope of the tangent line. That's the derivative, and that's given to you by the differential equation. So you do the tangent line, and the I'm using point slope form. I'm saying, hey, you know, delta y is approximately m times delta x. So delta x that's h in this case, and so you're just going to take the slope, multiply it by h, and then that's going to tell you how y has changed. I'll do another one that'll help. And so this now gives us a point that's close to being on the curve. It's not, but it's close. So now we're at this, I'm sorry, I wrote 1.1, I meant 2.1. So now we're at 2.1 comma 0.8.
Why is it 2.1?
Because I added 0.1 to the x value. That's what h is.
Oh, okay.
So the next one will be 2.2. We don't know what the y value is there. So and the next one will be 2.3, and the next one will be 2.4. This is a lot of work. This is like meant for computers, not people. Anyway, h stays the same. So now the slope is minus x over y. It's minus 2.1 over 0.8. Oh, I'm not going to do that in my head.
I was just waiting for you to walk. Okay, I will have no time and everything.
Oh no. 2.1 divided by 0.8 equals 2.65. 2.62. So it's 0.1, that's the distance times the slope, and the slope is 2.625. So now we'll be at 0.26 approximately. So now we'll be at 0.54. So I took the 0.8, subtracted the 0.26, and that now is the next point. So I have 3 points that are close to being on the curve. So this is clearly meant to be done. You can do it in Excel, but
What's that bottom star saying right there?
2.2, 0.54.
And where did you get the 0.54 from?
That's, I took 0.8 minus 0.26. So that was the slope is 2.625, but you're only going off delta x is point. The run is 0.1, so the rise is the run times the slope. And so this now gives you kind of a piece together solution, and it's not very accurate and it's very time consuming, but it gets the right idea. So let me run it like this, and we'll keep talking about these differential equation things on Friday.